So hello everyone. Today I will be sharing or I will be presenting some examples that involves our second law of thermodynamics. For the first one, we have a gasoline truck engine takes 10,000 joules of heat and delivers 2,000 joules of mechanical work per cycle. The heat is obtained by burning gasoline with heat of combustion L sub C equal to 5.0 times 10 raised to 4 joules per gram. What is the thermal efficiency of this engine? B. How much heat is discarded in each cycle? C. If engine goes through 25 cycles per second, what is its power output in watts? What about in horsepower? And for D, how much gasoline is burned in each cycle? To solve this problem, we will first write our given. We have QH, or from our hot reservoir, that's 10,000 joules. And then our work, that's 2,000 joules. Our LC, or the heat of combustion, 5.0 times 10 raised to 4 joules per gram. So for A, we are going to look for the thermal efficiency. So that's E. Okay. So you can notice here we have a little diagram, okay, of the process of the truck engine. So from the hot reservoir, that's 10,000 joules, and then it delivers 2,000 joules of work, and then what happens to the rest of the heat. Okay, so this is our QC. But for A, we will first look for the thermal efficiency of the engine. Now note that our thermal efficiency for engine is work divided by our QH, or our heat from the hot reservoir, dividing 2,000 joules by 10,000 joules, we will obtain 0.20, or this is equivalent to 20% na thermal efficiency. This is correct, but if it is more proper that our thermal efficiency is in percent form, so to convert it in percent form, you just multiply this by 100. Okay. So we have a thermal efficiency of this engine equal to 20%. Now for letter B, we are going to look for the heat discarded, okay, in each cycle, or our QC. This is our QC. So to solve this, we are going to use this formula. Work is equal to QH plus QC. So I will transpose this formula where QC will be left on one side. So QC is equal to work minus QH. Why work minus QH? If I will transpose this to the other side, since this is positive, pag ita-transpose ko siya sa kabilang side, magiging negative siya. Kaya nagkaroon tayo ng work minus QH. Now, substituting the given, we have 2,000 joules minus 10,000 joules, where this will give us negative 8,000 joules. So this is now our QC. Now the negative here indicates that the heat leaves the engine during each cycle. So we have 8,000, negative 8,000 joules as the heat discarded from the engine. Now for letter C, we are going to look for the power. Okay, the power output of the engine, given that we have 25 cycles per second. Okay, now to determine power is equivalent to work per cycle times cycles per second. This will be 2,000 joules per one cycle times 25 cycles per second per 1 second. Okay. So this is from the given, okay, dun sa problem natin or from the question. So you just multiply this. So cycles will cancel out. So this will give us 50,000 joules per second, or our unit for power is watts, okay, or 50,000 watts. Note that 1 watt is equivalent to 1 joules per second. So this is now our power. And then if we are going to convert it in horsepower, we have this following conversion that 1 horsepower is equivalent to 746 watts. So we are going to convert 50,000 watts to horsepower. It will look like this: 50 watts times 1 HP over 746 watts. So you just divide 50,000 by 746 watts. So watts here will cancel out. We will be left with horsepower. So 50,000 divided by 746 will give you 67. So our power in horsepower is equivalent to 67 horsepower. Now for letter D, we are looking for the amount of gasoline that was burned in each cycle. To look for the amount, that is actually our mass. Okay. So recall that in our previous discussion, our Q is equal to MLC. Okay. Yung previous examples natin, we're using lateral heat of fusion or L sub F, but in this case, we are using the combustion. Okay. So that is the reason why we have C. So in this case, QH is equal to MLC, or M is equal to QH over LC. So I will divide both sides by LC. Okay. You will obtain this one. So makakancel out siya. So M na lang matitira sa isang side. Now substituting our given, QH is 10,000 joules divided by our LC, that is 5 times 10 raised to 4 joules per gram. So joules will cancel out. We will be left with gram, okay, which is the unit for mass. We have 0.20 grams. So this is the amount of gasoline that was burned in each cycle, 0.20 grams. Now for the second example, we have during each cycle, a heat engine absorbs 2,000 joules of heat from a hot reservoir, thus work and exhaust 160 joules to a cold reservoir. What is the efficiency of the engine? Given the heat that was absorbed by the engine, our QH, that is 200 joules, Q sub C, that is 160 joules. Now we are going to look for the efficiency of the engine. Note that our efficiency is given with this formula, work divided by QH. Okay, so wala tayong work na given. Okay, so we have to look for the work. Okay. So since the formula for work is equal to QH minus QC, okay, we will just subtract the two in order for us to obtain the value for work. Okay, so 200 joules minus 160 joules. So this will give us 40 joules. Now we now have a value for work. So to solve for E, we will substitute work with 40 joules divided by our QH, that is 200 joules. So 40 divided by 200, that's 0.20 or 20%. So you just multiply this by 100 to obtain the percent form of the efficiency. So that is for this problem. Now, for the third example, we have a Carnot engine takes 2,000 joules of heat from a reservoir at 500 kelvins, does some work, and discards some heat to a reservoir at 350 kelvins. How much work does it do? How much heat is discarded? And what is its efficiency? So to solve for this problem, we will first write our given. We have QH equal to 2,000 joules, our temperature, that's 500 Kelvin for the hot reservoir, and our temperature for the cold reservoir is 350 Kelvin. Now we will have to calculate first the heat that was discarded, no, or our QC, since the formula for work is QH plus QC, or we don't have a value for QC, so we have to calculate first QC. To calculate for QC, we are going to use this formula, QC over QH equal to negative TC over TH. So this formula is actually the heat transfer in a Carnot engine. So we will transpose, or I will multiply QH in both sides, okay, para we will be left with QC in the left-hand side. So QH will be cancelled out. QC is now equal to negative, I'm sorry, this should be TC over TH. Sorry. So that should be TC over negative TC over TH times our QH. Okay. Now I will substitute our given. So that's negative 350 Kelvin divided by 500 Kelvin times 2000 joules. So our QC is equivalent to negative 1400 joules. So this is now our heat that was discarded in the engine, and we will now be able to calculate for work by adding QH and QC. So this is 2000 joules plus negative 1400 joules, we'll obtain 600 joules. So this is now our value for the work. Now what about the efficiency? So to calculate for the efficiency of a Carnot engine, we have 1 minus TC over TH equal to 1 minus TC is 350 Kelvin divided by 500 kelvins, will obtain 0.3, or this is 30%. So this is now our, or you can still use our formula for the efficiency, that is the work divided by QH. So this will be 600 joules divided by QH is 2000 joules. So you will still obtain 0.30 or 30%. So you can use both equation or both formula in solving our efficiency. So you will still obtain the same answer. Now for the fourth example, a steam engine works between a hot reservoir at 100 degrees Celsius, or that's 373 Kelvin, and a cold reservoir at 0 degrees Celsius, or 273 Kelvin. Now what is the maximum possible efficiency of this engine? And if the engine is run backwards as a refrigerator, what is its maximum coefficient of performance? Okay, now notice here that our temperature are converted into Kelvin. So in solving problems like this, you have to first convert your given problems or your given temperatures into Kelvin. So I will write the given for this problem, TC, that's 273 Kelvin, and our TH, which is 373 Kelvin. So here we are going to look for our efficiency, for the maximum possible efficiency of our engine. So our efficiency in terms of temperature is given by 1 minus TC over TH. So substituting the given, we will obtain 0.268 or 26.8% of efficiency. So this is the answer for A. For letter B, if the engine is run backwards, it will become a refrigerator. So what is the coefficient of performance? Now note that our coefficient of performance is given by QC over work. So in this case, we don't have a given value for work. So we will solve work in terms of our efficiency. So our efficiency is equivalent to work over QH. To solve for work, I will be multiplying both sides by QH. So this will cancel out. Okay, so our work becomes efficiency times QH. So now substituting this variable here, okay, we now have our coefficient of performance QC over EQH, okay, or QC QC over EQH, or this is just TC over ETH. Okay, so recall that we have this relationship of QC over QH is equal to TC over. Okay, so that is the reason why we can write this one as this one. So substituting now the values, we have 273 Kelvin over our efficiency. We will write it in decimal, okay, not in percentage, times 373 Kelvin. So this will give us 2.73. Now this is our coefficient of performance. This is for B, and then this is for A. For the fifth example, we are going to solve for the entropy. Okay, so the problem goes, what is the change of entropy of 1 kilogram ice that is melted reversibly at 273 Kelvin and converted to water at 273 Kelvin? The heat of fusion of water is L sub F equal to 3.34 times 10 raised to 5 joules per kilogram. So to solve this problem, we will first write our given. We have a mass that is 1 kilogram, our temperature that is 273 Kelvin, and our heat of fusion that is 3.34 times 10 raised to 5 joules per kilogram. Or our formula for entropy is delta S equal to Q over T. So recall that our Q can be written as M times LF. So calculating this MLF, we will substitute 1 kilogram times 3.34 times 10 raised to 5 joules per kilogram. So kilogram here will cancel out. Our Q now is 3.34 times 10 raised to 5 joules. So I will substitute it directly to our formula since we have now a value for Q. We have 3.34 times 10 raised to 5 joules divided by our temperature that is 273 Kelvin. This will give us 1.22 times 10 raised to 3 joules per Kelvin. So this is now our change in entropy. Okay. So the delta here indicates change, okay, or the word change in entropy. The entropy is indicated by big letter S. Okay, now for the last example, for the entropy, 1 kilogram of water at 0 degrees Celsius is heated to 100 degrees Celsius. Compute its change in entropy. Assume that the specific heat of water is constant at 4,190 joules per kilogram times Kelvin over this temperature range. Now, in this case, the difference between this problem and the previous problem is we have two temperatures. We have the 0 degree Celsius and the 100 degree Celsius. So we are going to use a slightly different formula, but conceptually it is similar. Okay, so I will write our given T1, 0 degrees Celsius, and T2, 100 degrees Celsius. So converting this into Kelvin, this is 273 Kelvin, this is 373 Kelvin. We have our mass that is 1 kilogram and our specific heat, okay, or our C, that is 4,190 joules per kilogram times Kelvin. Okay, so recall that we also have this formula in our previous discussions where Q is equal to MC delta T. Okay. And then the formula for our change in entropy could go like this. Okay. If we have two temperatures, we will use this formula for entropy, dq over T. Okay, so this is integration. Okay, so I will substitute Q, okay, with this. So our delta S becomes T1, T2, MC dt over T. Okay, so yung delta natin, napalitan siya ng letter D. Okay. Now, if you will be integrating this, okay, let's say we have MC and then the integration of T1 to T2 dt over T. If you will integrate this, you will actually obtain MC ln of T2 over T1. Okay, so I will leave it on your stock knowledge or your previous knowledge on your math, okay, or your calculus, I think. So I will directly substitute now our values. We have 1 kilogram for the mass or for M, and then our specific heat, which is 4190 joules per kilogram times Kelvin. Okay. Our Ln of our T2, that is 373 Kelvin and 273 Kelvin. So I think you can look for Ln button on your calculator. So calculating this, you will obtain 1.31 times 10 raised to 3 joules per Kelvin. So this Kelvin here will cancel out. The kilogram will cancel out. We'll be left with the unit J over K. So this is now our change in entropy for this problem. So those are some examples for this topic. If you have questions, clarifications, and suggestions, please feel free to approach me through my Facebook Messenger. Thank you for watching. Thank you for listening. God bless.